Tens of thousands of miles of steel tracks form the artery of a nation in motion. Behind this system lies a track-laying operation of immense complexity. Every rail, each weighing hundreds of kilograms, is placed with absolute exactitude. Why utilize fully automated machinery designed domestically? Standard tools might seem sufficient, but only specialized systems achieve the micron precision required. At first glance, the movement of these massive yellow giants seems slow, but in reality, it is calculated engineering. One can notice how they lift and align segments into a perfect geometry. The machines crawl forward, welding the pieces into seamless ribbons of steel. But this is just the beginning. The track-laying process continues its steady march. The steel artery expands further. 350 kilometers per hour is the speed Chinese trains reach, contrasting with the traditional United States method. Most American lines use thick layers of crushed stone, known as ballast, beneath each rail. Why rely on loose rock? It seems unstable, but in reality, it distributes the train's weight, maintains stability, and allows rainwater to drain away. But this is just the beginning of the divergence. China has taken a completely different path for next-generation high-speed railways. One can notice how the stone is replaced by a continuous concrete foundation known as slab track. Automated machinery fixes rails directly onto the surface. At first glance, it looks routine, but laser systems align the track so the structure becomes one unified body. It is stronger, more durable, and incredibly precise compared to stone. It does not end at this stage. Consequently, trains travel smoothly at velocities exceeding this high threshold. 7 million pounds of stone. This is the colossal weight of ballast required to stabilize just one single mile of railway track. Before these stones are even laid, construction crews prepare the subgrade by grading and compacting multiple layers of soil and gravel. Engineers work until a firm foundation is achieved, typically digging to a depth of about 2 to 4 feet, depending on the specific terrain and the expected loads from the trains. But this is just the beginning of the process. Why does the ballast layer remain unbound, unlike the rigid concrete structures around it? At first glance, a solid base would seem more durable and permanent, but in reality, the loose stone is necessary to absorb the intense vibration of passing trains and allow rainwater to drain freely through the track bed, preventing structural damage. Once the base is stable, engineers begin the massive task of spreading the ballast, releasing nearly 3,500 tons of material per mile from specialized hopper cars. The stones are then leveled evenly by a ballast regulator, a complex machine fitted with plow blades, rotating brushes, and laser-guided leveling boxes. One can notice how modern versions, produced by manufacturers such as Placer and Thorer, operate with minimal human input, automatically adjusting the height and slope within minutes. Construction crews move on to the next phase immediately after the ballast layer has been evenly distributed. Powerful vibratory compactors press the stone into place, creating a dense and perfectly stable foundation for the future line. Completing just 0.6 miles of track can take anywhere from several hours to a few days, depending on soil conditions and site terrain. It seems like a simple process of paving, but any error here would compromise the alignment of the entire railway. The foundation pieces that define and lock in the exact alignment of the track are the sleepers, which are positioned immediately after the base is ready. In most modern railway projects, this process is performed by an automatic sleeper-laying machine equipped with powerful hydraulic clamps. The machine lifts each sleeper, weighing between 600 and 700 pounds, and places it precisely according to its marked position. Each sleeper is spaced about 2 feet apart to ensure uniform load distribution. During a single shift, the automated machine can install more than 2,000 sleepers with remarkable accuracy. Sleepers can be manufactured from several materials, and traditional ones are made of wood pressure treated with creosote oil to prevent rot and reduce vibration. However, their lifespan is limited to around 20 to 30 years. Today, reinforced concrete sleepers have become the industry standard, as they are heavier, stronger, and capable of lasting over 50 years while supporting much greater loads. For maintenance or track renewal projects, engineers often use panel track systems, which consist of pre-assembled rail and sleeper sections built in factories. Once thousands of sleepers have been positioned with precision along the prepared route, the rail laying stage begins. Each steel rail, typically 78 to 80 feet long and weighing around 1,300 pounds, is delivered to the site on specialized transport vehicles known as rail trains. In modern railway construction, engineers often rely on continuous welded rails, or CWR, which are long steel segments pre-welded at the factory, each stretching up to 1/4 mile in length. At the work site, the rail train gradually feeds these immense steel ribbons from the rear. Hydraulic winches pull the rails forward and align them along the track bed with immense force. Workers guide the steel to glide smoothly over the ballast, positioning the rails perfectly atop each sleeper and holding them in place with temporary steel clips or pins. Once alignment is confirmed, the rail tensioning phase begins. Each rail is stretched or anchored using hydraulic tensioning machines to account for thermal expansion and contraction, a vital step that prevents future warping or buckling. After the rails have been perfectly aligned in place, the next step is to install the rail fastening system, a network of smaller components that keeps the entire track secure and stable. Each fastening assembly is made up of a steel base plate, rubber pad, spring clips, and anchor bolts. One can observe how the base plate evenly distributes the wheel load from passing trains across the sleeper, while the rubber pad beneath it cushions vibration and helps reduce noise. Workers move steadily along the track, fitting each set of fasteners into position. They tighten the bolts with torque wrenches to the precise specification, ensuring every joint applies the same uniform pressure. Once the bolts are secured, the clips are locked into place, holding the rail firmly against the base plate, while still allowing slight flexibility for thermal expansion and contraction as the steel responds to temperature changes. Transition to the next level of precision follows immediately. Once the entire fastening system has been installed, engineers move on to the stage of track alignment and ballast tamping. This is a precision process that determines how smoothly a train will glide over the rails. A specialized tamping machine travels slowly along the track at an average speed of 0.3 to 0.5 miles per hour, equipped with dozens of hydraulic vibrating tines. During operation, the machine lifts the entire rail sleeper assembly by about 1 to 2 inches. It is visible how the vibrating tines compact the ballast beneath at a rate of roughly 35 to 40 vibrations per second. This synchronized motion locks the crushed stones tightly together, creating a dense yet flexible foundation capable of absorbing impact and maintaining long-term track stability. Meanwhile, laser sensors and gyroscopes continuously measure elevation, tilt, and turn in alignment. Any deviation, even as small as 1/10 of an inch, is instantly detected, and the system automatically corrects it to match design standards. With this level of automation, a 1-mile section of track can be fully aligned and tamped in just 2 to 3 hours, making the process more than 10 times faster than traditional manual methods. Once the entire track has been precisely aligned, engineers proceed to the rail welding phase. Two main techniques are typically employed: flash butt welding and aluminothermic welding. In flash butt welding, the two rail ends are clamped tightly together by an electric welding machine. A powerful current passes through the joint, heating the steel to nearly 2,700 degrees Fahrenheit until it softens, melts, and fuses into a single continuous rail. In more confined or remote areas where access is limited, engineers rely on aluminothermic welding instead. In this process, a mixture of aluminum powder and iron oxide is ignited inside a cast iron mold. This triggers an exothermic reaction that can reach temperatures of up to 4,500 degrees Fahrenheit. This heat is intense enough to liquefy steel and fill the gap between the rail ends completely. Once the molten metal cools and solidifies, the excess material is trimmed off, and the joint is polished using a rail grinder. One can see the sparks fly as the machine removes any ridges or surface irregularities to ensure a perfectly smooth and seamless running surface. Once the entire rail line has been welded and ground smooth, the final inspection begins. Engineers use an ultrasonic flaw detector to scan the rails, detecting microscopic cracks or internal voids hidden deep within the steel that are invisible to the naked eye. A track geometry car then measures elevation, tilt, curvature, and gauge width with precision down to 0.02 inch. Any deviation beyond tolerance is corrected immediately using tamping and alignment machines. When all readings meet the standard, a test train is deployed to assess ride smoothness and vibration. It accelerates from 30 to 80 miles per hour, while hundreds of sensors record load and oscillation data. If the results fall within design limits, the railway is certified for operation, ensuring the line is ready to carry its first train with precision and stability. (2,900 degrees Fahrenheit is the temperature reached inside massive electric arc and blast furnaces, where the journey of a steel rail begins. It seems like a chaotic inferno, but here iron ore, coke, and additives transform into a uniform molten steel. Why is such extreme heat necessary for the mixture? At first glance, it looks like a simple melting process to liquefy the metal. But without maintaining this precise thermal threshold, the additives would not blend into a homogeneous stream capable of bearing thousands of tons of load daily. An automated feeding system measures each batch down to the pound to ensure consistency. Temperature sensors and spectrometers continuously monitor the chemical composition of the blend. One can notice how heat-resistant robots stir the molten metal to remove impurities, acting as mechanical arms in the scorching environment. Elements like manganese and chromium are introduced at exact moments to enhance strength and wear resistance. Once the desired composition is achieved, the molten steel is poured into molds, forming the foundation of ultra-durable rails. The material moves directly into the soaking pit, where heating chambers maintain temperatures between 2,200 and 2,300 degrees Fahrenheit. An automatically controlled combustion system regulates this environment to stabilize the internal structure of the billets. Infrared sensors monitor every surface point to ensure the metal does not cool too quickly. A sudden drop in temperature could cause surface cracking or deformation during the upcoming rolling stages. But this is just the beginning. Once stabilized, the billets move to the rolling preparation line. Massive heat-resistant rollers begin stretching and flattening the material under the regulation of high-power hydraulic motors. It seems like a brute force operation, but in reality, an electronic control center gathers data from dozens of sensors to fine-tune speed and force. This stage ensures the billets achieve a uniform size and sufficient ductility before entering the shaping process. Glowing red steel billets are fed into a continuous rolling line where they are gradually sculpted into the signature eye-shaped cross-section of a rail. The process begins with a roughing mill, where large diameter alloy steel rollers apply immense pressure to reduce thickness. In the intermediate stands, staggered rollers both press and rotate the billet, evenly distributing stress to prevent cracking. One can notice how high-pressure water jets remove oxide scales between stages while controlling the temperature. It gets more complex further on. The final stage uses precision grooved rollers to shape the eye profile down to the millimeter. Laser sensors continuously measure width, straightness, and contour, sending real-time feedback to the control center, which adjusts the roller gap during operation. A standout feature is the quick change roller system, allowing different rail profiles to be produced without halting the line. This provides an essential advantage in today's high-efficiency steel plants. As the rails exit the rolling section, they remain glowing hot and filled with internal stress. They immediately pass through a high-pressure water spray system where a dense mist envelopes the entire surface. Both the flow rate and spray speed are computer-controlled to ensure uniform cooling and prevent warping or distortion. Next, the rails enter the heat treatment zone, which includes quenching, tempering, or annealing furnaces operating between 900 and 1,100 degrees Fahrenheit. And this is not the limit. The combination of rapid cooling followed by precise heat treatment increases hardness. This process improves fatigue resistance and preserves the sharp I-beam profile, creating a thick head for load bearing, a slender web, and a broad base. Thanks to this technology, each rail can endure millions of loading cycles without deformation. This is a critical requirement for the reliability and longevity of high-speed railway lines. After heat treatment, individual steel rails transfer to the welding line to form continuous seamless tracks stretching hundreds of feet in length. A system of guide rollers and laser sensors aligns the rail ends with sub-100th inch precision, specifically within 0.01 inches. Flash butt welding technology uses a powerful electric current to heat both ends to over 2,700 degrees Fahrenheit. The metal fuses into a single solid piece under immense pressure, after which an automatic grinding machine removes excess material. Everything only gets more complicated. The entire operation is monitored through a central control panel. Finished rails transfer to the automated inspection area, where high-speed cameras and optical sensors scan the entire surface at microscopic resolution. Ultrasonic and X-ray systems examine the internal metal structure, automatically rejecting any rail that fails to meet specifications. Random samples are tested using tensile machines, compression rigs, and Rockwell hardness testers to evaluate load-bearing capacity. Each rail that passes inspection is laser marked with a traceable identification code, ensuring full production transparency before shipment. Two steel lines mark that the railway track is built. Why was the entire process detailed? The path looks ready because hidden precision ensures safety. At first glance, the result seems simple, but in reality, it is complex. One can notice the rigid alignment, but this is just the beginning. More fascinating stories await.